So, welcome to this class on neuroscience of human movement. In this class, we will be talking about skeletal muscles. This is part 2 of our discussion on skeletal muscles. So, in this class, we will be talking about types of contractions, twitch contractions and tetanic contractions, also called as smooth tetanus. So, this is also called as tetanic contractions or smooth tetanus. So, essentially each contraction is not necessarily smooth, but when multiple contractions add up is part of today's class. Okay. So, let us look at what happens when a single action potential arrives at the neuromuscular junction. When a single action potential arrives at the neuromuscular junction and it causes a single action potential in the postsynaptic muscle fiber, say for example, one action potential at the neuronal end causes one action potential at the muscle fiber, and this reaches say the T tubule, and through the interaction of DHP receptors and the ryanodine receptors, calcium is released, and this causes release of this action potential when it reaches the T tubules through interaction of DHP receptors and ryanodine receptors, calcium is released, and this release of calcium somehow causes the contraction, and this can happen only in the presence of ATP. So, there are two essential things for muscle to contract or sarcomere to contract. These are ATP and calcium ions, right. This is the situation. Now, if a single action potential arrives at the neuronal end and reaches the muscle fiber and reaches the T tubule terminal cisternae, then some amount of calcium is released. This presence of calcium is sufficient to move the troponin in the troponin tropomyosin complex in such a way that actin and myosin can then interact, right. That causes an increase in force. Let us remember how that happens. How that happens is the myosin attaches to the binding sites on actin and then pulls in such a way that the Z disc, suppose this is one Z disc and this is another Z disc, and suppose the thin filaments are in red, okay, the thin filaments are in red of the order of about 2 piconewtons is produced, right. We saw this. Now, suppose for the calcium is depleted, suppose the action potential arrival has stopped, then what happens, the calcium is taken from the intracellular matrix to the sarcoplasmic reticulum through an active process called as calcium ATPase. We saw this in the previous class, is it not? So, when calcium is taken back, what happens, there is no more calcium that is available to continue the cross bridge cycles. Look, the cross bridge cycle is going to continue as long as both energy in the form of ATP and calcium are present. As long as calcium and energy are present, there is going to be continued contraction that is going to happen until and unless calcium is withdrawn, right. So, when the action potential is not there, then what happens, the ryanodine receptors close and then the calcium ATPase continues to pump the calcium from the intracellular matrix of the muscle to the sarcoplasmic reticulum, once again within the muscle. It is a storage house. We also saw how that is getting stored due to the presence of the special protein calciquestrin, right. We saw this. So, when calcium is getting depleted, then what happens, the sarcomeres are no longer able to produce force or continue the cross bridge cycle. Then that leads to a reduction in force. Of course, since this is a physical and physiological process, it is not like once the calcium is withdrawn, the force will immediately come down to 0. There is no instantaneous drop in the force. There is a slow withdrawal of force and then it comes down. Obviously, this depends on two things. There are two things that dictate whether the force level will sustain or whether it can increase. What are the various things that could affect this? An important point is how long does it take for the force to be developed, right. This is called as the contraction time. Okay. So, this varies between fibers, between muscles, between individuals. This can be, with a lot of practice, trained to be shorter, etc. right. So, the contraction time is something that dictates for how long is it going to take for the fiber or for the sarcomere to develop the force. Now, if suppose another action potential arrives here before the contraction time has been elapsed, then it is possible for you to either sustain the force or to continue developing the force. But in the particular case that we are now discussing, then calcium ATPase is continuing to do its job, then what happens, the force continues to decline and then reach the original rest state approximately. So, one is the contraction time, the other is the arrival of action potential before the contraction time elapses. Suppose there is the stimulus or the action potential is given here and then the next stimulus is given say there, then what happens, then there is going to be a small gap. Note, between the stimulus arrival at the neuronal end and the development of contraction, there is a small delta t time that elapses, that also elapses in this case, and then there will be a development of force. Okay. What causes this delta t? Let us remind ourselves, when we are talking about the stimulus, we are talking about an electrical event, we are talking about an ionic event, is it not? Whereas contraction is referring to a mechanical event. In general, in these cases, the mechanical event is preceded by the electrical event. First the stimulus arrives and then the actual force production or the actual displacement or the actual reduction in sarcomere length or the distance between the Z discs. Just for clarity I am going to draw it like this. The actual reduction in Z disc follows the electrical event. Okay. So, because this is a physical phenomenon, there needs to be some time that needs to elapse, and also the interaction, the release of calcium and the interaction of troponin, tropomyosin, all these things take some non-zero time, some time it takes for these reactions to happen, for these chemical reactions to happen, then cause the mechanical event. Okay. So, as I said, if the next stimulus is arriving at that point, then the next contraction will be developing here. The force has gone back to the initial force or to some baseline force level. This need not be 0. For practical purposes, we can assume this force to be 0, but this need not exactly be 0, right. So, if for example, I move this stimulus a little bit to the left, say for example to here, then what happens, the force will start developing. After again there will be a delta t time that will be required for development of force again here. Here there is already some force, these two could add up. So, in twitch contractions you have development of force and then drop of force, but before the force drops, if another stimulus arrives, then it is possible for the new force to get added to the previous force. Of course, this depends on two important factors. One is contraction time, this is unique maybe for each sarcomere or at least for each myofibril. So, this varies between muscles, this varies between people, this varies between groups of individuals, this varies as a function of age, this varies as a function of disease, etc. Right. Second is the rate of action potentials. So, if action potentials are arriving very fast, then there is going to be a greater chance that two force levels are going to sum up, right. If they are coming sufficiently farther in time, right. If the two action potential are farther away in time, then what happens, one action potential force cannot be increased beyond the original twitch related force level, right. So, both of these are crucial. So, suppose in this case there are multiple consecutive action potentials arriving and they are sufficiently close in time, then the before this twitch can go back to 0, the other twitch has arrived and that causes an increase in the force level, and before that could die down, another action potential has arrived and that causes another twitch, etc. Thus essentially by the end of this, as in some delta t after the arrival of the last action potential, you are having essentially that much force developed. So much is the increase in the force level, right. Now, how to maintain that, how to do that, that is the question. It turns out then if for example then I keep increasing the stimulation frequency to a much higher value, say for example like that, much higher value, right, then what happens essentially is that this force level is reached and then it is maintained. Actually, if you zoom in, what you will see is small variations in forces at that level also, but depending on the resolution of the drawing it might appear to be constant. There are going to be small variability, there is going to be some variability here. Note that the blips in the tetanus here, even just below the tetanic contraction here, are due to the peaks of twitch peak, right. Essentially here also this may be due to twitch. For this to happen you need a sufficiently large frequency, sufficiently high frequency, right, of stimulation. At that level you are going to have tetanic contraction, below that level you are going to have an increase in force, much below that level you are going to have a twitch and then a drop in force to approximately the baseline level, okay. So, once again here after the tetanic contraction is developed, what you are having is a force level that is higher by some delta f above the baseline level, okay. The force produced by the fiber or by the fibril, by one myofibril, right. One myofibril is composed of multiple sarcomeres in series, whereas one fiber is composed of multiple myofibrils in parallel. This is what we have seen in the previous class, right. So, there are several things that are of interest. One is force that is produced by a myofibril, force of a myofibril. Turns out that the force of a myofibril is proportional to the average sarcomere force, but not the number of sarcomeres. So, having a large number of sarcomeres does not increase the force, but having sarcomeres that can produce a higher average force will increase the force. So, it is important to note the difference, right. However, if you have a relatively large number of sarcomeres in series in a myofibril, in a different myofibril you have a relatively small number of sarcomeres. A question is, what is the advantage of having a larger number of sarcomeres in a muscle fiber? It turns out that the maximal shortening velocity means in this case not velocity of movement, in this case we are talking about velocity of shortening, time rate of change of contraction displacement, not the actual movement related displacement. So, now when I am moving my arm, that is movement related displacement, and there is a velocity of movement. Here when I refer to this velocity, I am referring to contraction velocity, right. It turns out that the maximum shortening velocity of a myofibril is proportional to number of sarcomeres. So, having a number of sarcomeres, having a higher number of sarcomeres has an important positive consequence. Then you can develop the force at a higher rate, you can develop it quickly enough, right. So, that depends on the number of sarcomeres, but not the force level itself, very important to distinguish the two, alright. And then the other point is, what about the force? When I am talking about fiber, I am referring to several myofibrils in parallel, is it not? This is proportional to the number of sarcomeres, not in series. Here this is in series, here this is the force produced by a fiber is proportional to number of sarcomeres in parallel, okay. So, that means if I had a larger number of sarcomeres in parallel, essentially what does that mean? That means the diameter, this is looking at it from that dimension, muscle size itself, is it not? So, as the diameter of the muscle increases, you are going to have a larger force. Actually, there are other details such as what particular area are you referring to, and it turns out that the max force produced by a muscle is proportional to physiological cross sectional area, that also is in agreement with this principle that we have just now discussed. So, basically the physiological cross sectional area refers to the area due to the number of fibers, as in the area that is perpendicular, that is found orthogonal by cutting the by making a cut orthogonal to the direction of movement, direction of the fibers themselves, right. Now, that is also similar to finding the number of sarcomeres in parallel, is it not? So, then you have maximum force that is proportional to the physiological cross sectional area. This is a known fact, and that agrees with this fact that we have seen, alright. So, there is a different cross sectional area that is discussed in biomechanics, that is what is called as the anatomical cross sectional area. It turns out that this is different from the physiological cross sectional area. I will leave the details for a future class, or interested readers can actually check that in future. With this we come to the end of this class. So, in summary, we have seen types of muscle contractions, we have seen twitch, we have seen smooth tetanus, and we have also seen details about what causes maximum shortening velocity and what causes force of a myofibril, as in what influences that and what influences force in a fiber, etc., right. So, this is proportional to number of sarcomeres in series. Force of a myofibril is actually proportional to the average sarcomere force, not the number of sarcomeres. Of course, force of a muscle is proportional to the in future classes. So, with this we come to the end of this lecture. Thank you very much for your attention.